Okay, so this is a great time to talk about how we use evidence to determine the type of particle attraction that is being observed with a compound, and what causes things like vapor pressure and um, um, enthalpies of vaporization and enthalpies of fusion. If you you already have this paper that you're seeing right now. If you will go to the website and make sure you print out the paper that has the heating curve on it, as well as the vapor pressure graph. I'd like to speak about that as well. And make sure you have your IPF examples. I think that is on the back of your interparticle attraction sheet. So what we have here are several compounds that we have some data about. If we look at the first box here, we can see that we have some compounds that have some really high melting points here, and some with a little bit lower. Notice that these compounds are of the same type. So we notice, first of all, that these are ionic compounds. And you might be given some data like this and asked to explain the phenomenon that is observed. So what we can see here is that we have ionic crystals. We know that the strength of an ionic compound or the melting point of an ionic compound depends on lattice energy. So we can look at this and say, okay, there's two things we want to explain. We want to explain why the potassium chloride and the sodium chloride are much lower melting points than the sodium oxide and the magnesium oxide. So we want to explain this phenomenon. And then we also want to explain why magnesium oxide has a higher melting point than sodium oxide, and why sodium chloride has a higher melting point than potassium chloride. So you should pause and think about this for a minute. Kind of formulate what you think. We know that lattice energy depends on size and charge product. So pause and think. Maybe jot down a few notes about how you would describe these phenomenon and why they occur. Okay, so I hope you've come back after thinking. So clearly what we see here is that potassium chloride and sodium chloride have much lower melting points than sodium oxide and magnesium oxide, and that is because the charge product is less. We have a charge product on those compounds of 1, whereas the sodium oxide and magnesium oxide have a charge product greater than 1. So here the charge product, Q1, Q2, is only 1, which leads to a weaker lattice energy. Here we have a charge product for the sodium oxide of 2 and a charge product for the magnesium oxide of 4. And that describes why magnesium oxide is a much, much higher melting point than the sodium oxide. Next little example here, we have a couple of metals, right? So the crystal type is a metal. And we can see we have potassium with a melting point of 337 and calcium with a melting point of 1110. And this is what we know. Metallic crystals are attracted by a metallic bond. In the notes, you learned that metallic bonds, the strength increases as the number of valence electrons that are contributed to the mobile sea of electrons increases. So here we have calcium with 2 valence electrons and forming a 2+ ion, versus potassium with 1 valence electron forming a 1+ ion. A 2+ ion is going to be more attracted to the sea of delocalized electrons than the 1+ ion will. And therefore calcium is going to have a stronger particle attraction and a higher melting point. Here we have some covalent compounds. So we're looking here at molecular crystals. And we can first of all see that all of these boiling points, these aren't even melting points, these are boiling points. And look how low they are. And we compare these boiling points to the melting points of the ionic crystals or the metallic crystal. These are just like really, really low. So we want to make sure that we know that ionic compounds, right, are always going to melt and boil at much higher temperatures than covalent. But here, so you might, if you're given all of this data, that's certainly something you'd want to explain the difference there between those negative numbers and then the really high positive numbers that we've seen previously. But if we look at this, if we look at these compounds, with molecular compounds, you have to be a little bit, go into more detail a little bit. So we want to draw some dot structures here. Nitrogen is a nonpolar compound. And the reason this compound is nonpolar is because the nitrogen-nitrogen bond polarity is nonpolar, whereas carbon monoxide, with the same triple bond and linear dot structure or linear geometry, the electron density shifts strongly towards the oxygen, creating a dipole moment, and that molecule is polar. So we can see that the carbon monoxide is showing a higher melting or higher boiling point than the nitrogen because it is a polar compound. Yes, negative 192 is higher than 196. Negative 196. So polar compounds exhibit dipole forces, dipole attractions, which are much stronger than the London dispersion attractions that are present in that nonpolar nitrogen compound. So then we have the tetrahedron of the silicon tetrahydride. And we know that this is a tetrahedral with no lone pair. This is a nonpolar molecule. Even if the bond is polar, which we would assume it is, we assume all bonds are polar unless it is diatomic or if it is a carbon-hydrogen bond. So we've got this nonpolar molecule versus a phosphorus trihydride, which has a lone pair there, and we're assuming polar bonds, so we would assume that's a polar molecule. And the data would indicate that as well. We know that polar molecules are attracted with dipole forces. Nonpolar molecules are attracted with London dispersion forces. London dispersion forces are weaker than dipole. So we would expect that silicon tetrahydride to have a lower boiling point than the phosphorus trihydride, and it does. Negative 112 is a lower temperature than negative 88. All right, this last little example here. What we have, these should be connected to each other, and then anywhere there's a dash, there should be a hydrogen. So this would be filled with hydrogens. This would be filled with hydrogens. These are two different structures for the same formula, C5H12. And that is what we call an isomer. Isomers are compounds that have the same chemical formula, but they have a different structure. So clearly what we can see here is that this isomer, where we have a shorter 3-carbon chain, so this has a chain of 3 carbons alone, right? This is 3 in this direction, 3 in this direction, versus a chain of 5 carbons straight. The chain that has the straight carbons has a much higher boiling point than the chain that only has 3 carbons. So we know that the longer the carbon chain, based on this data, that's going to equal stronger London dispersion interactions. We know that these are London dispersion interactions because the carbon-hydrogen bond is a nonpolar bond. Okay. So a couple things I might want to add here that I forgot to put on this sheet are how do alcohols and acids compare. So the longer is stronger rule applies also to acids with a few exceptions. And then alcohols and acid solubility. So longer and stronger when it comes to melting point with acids and alcohols, except if we're talking about solubility. And then it's like, because we're stuffing the water molecules with those compounds, the smaller acids are more soluble than the larger ones. The same thing for the alcohol. So the larger those compounds get, the less soluble they become. Okay, why don't you take a minute to do your IPF examples. All right, let's just do them together really quick. So this is saying, okay, which of the following has the lowest boiling point? And here we have a carbon chain that is 2 carbons versus a carbon chain that is 1, 2, 3, 4 carbons. Longer is stronger, so the carbon chain with fewer carbons has the lower boiling point. The highest freezing point is going to be the one with the strongest attractions. Water is polar, and it is a molecule. Sodium chloride is ionic. Methane is a nonpolar molecule. And we know that ionic compounds always have higher melting and boiling points than covalent. So don't get crazy because melting point and freezing point are the same thing. Sometimes students get confused. They're like, but wait a minute, it's freezing point. But the melting temperature and the freezing temperature are exactly the same. Just think of it in terms of melting point. The greatest vapor pressure, we know that higher vapor pressures occur with weaker interparticle attractions. So we're looking here at a metal, another metal, water, which is a molecule and it is polar, and we have a carbon chain dispersion. We know that not only is water a polar molecule, but it has that really strong dipole attraction that we call a hydrogen bond. So we know that metals do not have much vapor pressure. We can't smell a metal. Metals are pretty strong. We can rule those out. And then we have water compared to the dispersion attractions of that carbon chain. The carbon chain is going to have the weaker interparticle attraction. Lowest melting point. Think about it for a minute. This is the nonpolar nitrogen molecule. Remember that carbon monoxide is polar. This is ionic. Carbon dioxide is a nonpolar molecule, but it's a larger molecule. So it's going to have it's got more electrons, so it's going to have a greater London dispersion attraction, and therefore With more electrons, it has a stronger London dispersion attraction and therefore a lower melting point. Number 5, this should be bonded here. Nitrogen bonded to the hydrogen, and there's a lone pair up there. Think about it. The answer to this question is water, and it's simply because it has 2 hydrogen bonding plate points on that oxygen with its lone pair. There's 2 places to hydrogen bond, whereas on this compound, there's only this one place to hydrogen bond. Smaller enthalpy of vaporization. So the smallest enthalpy of vaporization is going to be the strongest, weakest interparticle attraction. So we've got a long carbon chain, a smaller one, and a smaller yet. Longer is stronger, so the smallest is the weakest. Largest enthalpy of fusion. Hydrogen bond interaction. This is London dispersion. Ionic, so that's lattice energy with a charge product of 4. And this is lattice energy with a charge product of 2. The largest enthalpy of fusion means the strongest attraction. So the strongest attraction here is, of course, the ionic magnesium oxide. So in this last thing, we have this oxygen, which is double bonded to this carbon here. That's a ketone. The lowest vapor pressure. Lowest vapor pressure is stronger attraction, stronger interparticle force. So here we have a carbon chain of 1, 2, 3 carbons, 1, 2, 3 carbons, and that hydroxyl group creates a polarity on the end of that carbon chain. So you end up with that C double bonded to O, and then that oxygen has some lone pair on it. That creates a dipole moment. That's why alcohols are soluble in water. And then here we also have oxygen with a couple of lone pair. Typically in organic compound, wherever there's an oxygen, there's a bend in the compound, and that makes the compound polar. But here we have a carbon chain that is only 1, 2, 3 carbons. And here the carbon chain is 1, 2, 3 carbons. But this hydroxyl group is really kind of what gives it away. This compound is a much stronger compound with its hydrogen bond. You have that OH bond, which turns our dipole into that special dipole, the hydrogen bond dipole. So this is going to be the strongest interparticle attraction, and therefore the lowest vapor pressure. Take a minute to print the problem set that says interparticle attractions, and you may work on that.